Here's a problem. A polynomial has three roots. One of them is 3 on 2. The other is minus 5 with multiplicity 2. Also, it has a remainder of minus 7 when divided by x minus 2. How do we find our polynomial? Well, first, let's have a look at the number of roots it has. It has 3 roots. So we're probably thinking that this is going to be a cubic. So it's going to have a highest power of 3 for the variable x. So it's a polynomial of degree 3. Now, just having a look at a set of axes for a moment, we're told that one of the roots has multiplicity 2. Typically what this means is that if we take a small section of the polynomial, if we look from above, it will come down, touch the x-axis, and then rise up again. Or if it comes from below, it will reach upwards, touch the x-axis again, and come down. That's what we're looking for when we see a polynomial where one of the roots is of degree 2. So getting back to our model, our generic model will be y equals ax cubed plus bx squared plus cx plus d. That's the most general model for a polynomial of degree 3, where we work out by various conditions given what those constants are, a, b, c, and d. Another way of writing this is as follows: y is equal to x minus xo, where xo is one root, x minus x1, where x1 is another root, and x minus x2, where x2 is the third root for a polynomial of degree 3. So let's go on to the next step. Here's an image of a cubic. Notice that the cubics generally have a local maxima and a local minima, beyond which they shoot off to infinity and minus infinity at each end. And in this case, as with many, they will cross the x-axis, the horizontal axis, in 3 places. This one crosses at minus 4, minus 1, and 2. So we know that when we plug those values in to this cubic's equation, we'll get f of minus 4 equals f of minus 1 equals f of 2, which equals 0, because that's the value of the cubic at those x values. Now we're told in our problem that we have 2 roots, 3 on 2 and minus 5. So when we plug those into our equation, of which we've got the generic equation ax cubed plus bx squared plus cx plus d, we know that those will become equal to 0. So if we work those out now, we get the following. On the left hand side, we'll assign that for the root minus 5, we get a times minus 5 cubed plus b times minus 5 squared plus c times minus 5 plus d is equal to 0, because minus 5 is a root, which leaves us with minus 125a plus 25b minus 5c plus d equals 0. On the right hand side, plugging in the root of 3 over 2, we end up with 27 over 8 times a plus 9 over 4 times b plus 3 over 2 times c plus d equals 0. So from here, we'll move on now to looking at the remainder of x minus 2. So now we're going to carry out the long division of a polynomial by another polynomial in order to find out what our remainder is. We know that when we divide this polynomial by x minus 2, we have a remainder of 7. So let's perform that long division now. So we have under the under the division sign, ax cubed plus bx squared plus cx plus d. Now the reason I've left those gaps there between the different terms in that polynomial are because we'll have some large coefficients as we do this division. So we have our divisor, x minus 2. We start by taking that into the first term, ax cubed. So x minus 2 into ax cubed. So what we do is we take the first term of x minus 2, x, and we divide it into ax cubed, and it goes ax squared times. So the ax squared goes above the bx squared term in that expression. And now we multiply that quotient term by the divisor, and we get ax squared times x minus 2, which is ax cubed minus 2ax squared. Now we do our subtraction. So we have ax cubed minus ax cubed, 0. And we have bx squared minus 2ax squared. So that's bx squared plus 2ax squared. So now the term, or the coefficient for our x squared term, is b plus 2a. So b plus 2ax squared plus, bringing down the cx. Now again we repeat. So we divide x minus 2 into b plus 2ax squared plus cx. So x goes into b plus 2ax squared, b plus 2a times. So we have the second term of our quotient, b plus 2ax. Now we multiply that by the divisor again, b plus 2ax times x minus 2. That gives us b plus 2ax squared minus, bracket, 2b plus 4a, bracket, x. So now we do our subtraction again. So b plus 2ax squared minus b plus 2ax squared is 0. So the only difference we'll have is with the x coefficients. So we have c minus 2b plus 4a. So that gives us c plus, bracket, 2b plus 4a, which is 4a plus 2b plus cx. Bring down the d. Now, again, we divide the divisor into the first term there. How many times does x go into 4a plus 2b plus c times x? Well, it goes in 4a plus 2b plus c times. So that becomes the next term in our quotient. And we put that above the d. So that becomes the constant term of our quotient. Now, we multiply that term by the divisor, x minus 2. So we get 4a plus 2b plus c times x minus 2 lots of that, which is minus, bracket, 8a plus 4b plus 2c, bracket. And we do our final subtraction to get the remainder. Bear in mind that the remainder is minus 7. So what do we get? We have d minus 8a plus 4b plus 2c. So that gives us 8a plus 4b plus 2c plus d, which is equal to minus 7. The question to now ask is, can we now solve our problem? We know that minus 5 is a root, which gave us this equation. We know that 3 over 2 is a root, which gave us this equation. And through all of the work we did on the previous slide, we know that a remainder of minus 7 when divided by x minus 2 gave us this equation. Can we solve our problem? Well, we have 4 unknowns and 3 equations. So no, we don't have enough information. But consider the following. Expressing a polynomial as a product of its roots. We saw this in our first slide when I presented it. For a polynomial of degree 3, we can express it in the following way. Y is equal to a, which is a constant, times x minus x naught, times x minus x1, times x minus x2, where the roots of this polynomial are x naught, x1, and x2. So what we have is y is equal to a into x minus 3 over 2 times x plus 5 squared, y plus 5. Well, the root is minus 5, and we have x minus the root. X minus minus 5 is x plus 5. And because that's a root of multiplicity 2, we can square that term. So those are the roots, 3 over 2 minus 5 with multiplicity 2, and a is an adjusting coefficient for the cubic term. So on this slide, following on from the last slide, we have y is equal to a into x minus 3 on 2 times x plus 5 times x plus 5. Let's multiply that out. So multiplying the last two terms out, we get y is equal to a into x minus 3 on 2 times x squared plus 10x plus 25, which for the final line will give y is equal to ax cubed plus 17 on 2 ax squared plus 10ax minus 75 on 2a. So now that we've established our polynomial by multiplying out the factored root form, let's divide that by x minus 2 and see what the result is. So because we've done this once before, we're not going to go through this in such detail, so we'll go through it more rapidly. So under the root sign you can say see ax cubed plus 17 on 2 ax squared plus 10ax minus 75 on 2a, and that's being divided by x minus 2. So first x minus 2 into the ax cubed term. How many times does x go into ax cubed? That would be ax squared, so that becomes the first term of the quotient, going above the x squared term and the dividend. Now multiply that quotient term by the divisor. Ax squared times x minus 2 gives us ax cubed minus 2ax squared. Subtracting that from what's above, the x cubed term disappears and we have 17 on 2ax squared minus 2ax squared, which gives us 21 on 2ax squared plus 10ax, bringing the 10ax down. Now, how many times does x go into 21 on 2ax squared? Well, 21 on 2ax times. So that's the next term in that expression for the quotient above. So that goes above the 10ax and the dividend. Now we multiply that quotient term by the divisor. So 21 on 2ax times x minus 2, which gives us 21 on 2ax squared minus 21ax. Now subtract that from what's above it. So the x squared terms cancel out and we're left with just the x term, 10ax minus 21ax, which is 31ax, and we bring down the constant term. So we have 31ax minus 75 on 2a. Now, how many times does x go into 31ax? That would be 31a times. So that's the last term for the quotient, and that goes above the 75 on 2a in the dividend. So, multiplying the 31a by the divisor, x minus 2, we get 31ax minus 62a. Now we subtract that from what's above it to get our remainder, which, remember, is equal to minus 7, and that gives us 49 on 2a is equal to minus 7. And we can solve that for a. So a is equal to 2 over 49 times minus 7, which equals minus 14 on 49. Guess what? Before we had 4 unknowns with only 3 equations, but now we've been given one of those unknowns. So that means we have 3 unknowns and 3 equations, and we'll be able to solve those for a unique solution for those coefficients so that we can find the unique cubic that satisfies the conditions that we want. From our previous slide, we got a value for a, minus 14 on 49, which by the way simplifies to minus 2 over 7. So let's extract the equations that we came up with. So the first one was minus 125a plus 25b minus 5c plus d is equal to 0. Second equation, which was for the root of 3 on 2, we have 27 on 8a plus 9 on 4b plus 3 on 2c plus d equals 0. Third equation, 8a plus 4b plus 2c plus d equals minus 7. That was by way of finding that we had minus 7 remainder when dividing our general polynomial, or our generic polynomial, by x minus 2. Fourth equation, a is equal to minus 14 on 49, which is minus 2 over 7. I haven't simplified it. That came by way of dividing our factorized polynomial with the roots as factors, dividing that by x minus 2 and getting a result of minus 7. Now, what I can do to the above is present it like this, here below. What I've done is I've separated out the coefficients of a, b, c, and d and presented them in matrix form. So that 4 by 4 matrix multiplies into that column vector to give the left-hand side. That is the side on the left-hand side of the equals sign above. And on the right-hand side, if you look above, we've got going downwards 0, 0, minus 7, minus 14 on 49. Well, that's on the right-hand side here. So all I need to do now is just use an online row reduction calculator, and I can then get the value of all my coefficients, which can be done in a couple of seconds. So I'll present that on the next slide. Starting with where we left off, our coefficient matrix there, column vector, and on the right hand side solution vector. After doing row reduction, we get our identity matrix on the left, indicating the values of A, B, C, and D, which are going downwards: minus 2 over 7, minus 17 over 7, minus 20 over 7, and 75 over 7. So notice that minus 2 over 7 for A, that's just a simplification of minus 14 over 49. So now we can write our polynomial and we'll have a look at it. Just a short note, that row reduction was done by way of a calculator that was found on the website for emathhelp.net, listed below there. So reading out our polynomial, we have y is equal to minus 2 over 7 x cubed, minus 17 over 7 x squared, minus 20 over 7 x, plus 75 over 7. And just to verify that it meets at least one or two of the conditions that were initially laid out, I've graphed it here on Desmos using Desmos graphing calculator. Here's a screen capture of that, and we can see that because the leading variable x cubed has a negative coefficient, as we go towards negative infinity for x values, it rises to positive infinity, and as we go towards positive infinity in the way of x values, this polynomial descends to negative infinity, which is about right. And we can see indeed minus 5 is a root of multiplicity 2 because it's being touched here by the curve, and it cuts through 3 over 2, which is a root of multiplicity 1. So that looks exactly like we have the right polynomial. Thank you very much for watching and listening. Hopefully this was helpful and gives some idea of how this works. Please feel free to subscribe and to like, and more content will be coming soon. Thank you.